Good morning. How are you? Alrighty. So my connection is going to be pretty bad. I'm still downloading the video from the morning class. So for right now, let's just see who we have in the room here. So this one we have the cotton ball, who gets very mad if I'm not petting him. So you may hear him growl if I stop. Let's see, who else do we have here? We've got 3 more chihuahuas. So on the left there, we have Oz, who's my oldest. We have Kaz, who's in the middle. He's afraid of everything. And then you guys remember AJ, the pirate from last time. So we can see this dude is now just begging for attention. Alrighty, so looks like I have finished downloading. Hi, dude. I'm going to put you down now, okay? He's not happy with that. Alrighty, so 10:15, looks like we're right on time. One announcement, just to get this out of the way. Probably next week we will have class on Thursday. So if you can, just be aware that I will be live on Thursday. If not, if you can't make it, of course, it will still be recorded and everything. You could always watch it later. Just letting you know there will be a video for Thursday next week. Okay? Just to make sure. Alrighty. So, hooray. One day I'll remember to change the title. It's always going to say Chemistry Day 1, I guess. Whatever. That's okay. Let's see. Before we actually begin chemistry, did anybody have any other questions about syllabus, textbooks, whatever, something like that? Okay, I am not seeing anything. So, here we go. I do have one more question. So it does look like all of you have taken some sort of chemistry before. So I'm going to kind of skip the scientific method explanation. If you really like, I can post a little short video about it. Or you can watch my Chem 101 little blurb about that. So just to skip over some of the less interesting stuff. So, chemistry, we are here to study 2 things. This is what chemistry is all about. So chemistry, study of matter and energy. Biology, of course, study of life. You have geology, study of the earth. Chemistry is a study of matter and energy. And we're going to be talking about both of these things quite a bit this semester. So let's see if any of you can remember some of the 2 things that matter has that energy does not. What makes matter matter? There are 2 properties that we have here that matter has. Okay, I will perhaps prompt us. So it takes up space, right? Anything that is matter will take up space. So coffee mug, matter, takes up space, right? I cannot put, let's see, I cannot put my gigantic box of goldfish into my coffee mug, right? They cannot occupy the same space at the same time. Does not work that way. I cannot squish all my dogs together into some massive super dog, at least in real life. If this was a cartoon, whatever, I could totally do that. But because things take up space, they cannot occupy the same space at the same time. And yeah, the other one is going to be, has mass, right? Oops, has. Has mass, right? That just means there's some amount. So if we were to count all of the, water molecules in my coffee here, we could do that. We could say, okay, It would take a very long time, but we could do that. We could see how many water molecules are in this coffee mug. We could also see how many different, calcium atoms there are in the entire coffee mug or whatever. We can figure this stuff out. There's an amount of it. There's a mass of it. So we can quantify it. All right, energy does not have these things. So energy does not have a volume, does not take up any space, and also does not have any mass. So we can put a ton of energy in one space at one time because it does not take up space. So we can have, lasers, which are very high levels of energy, versus something like, a flashlight or a light bulb. These are relatively low sources of energy. We can put, they can occupy the same space at the same time. And they don't have mass either. Alrighty, so can I get some examples of each? Does anybody have any examples of matter? This should be very easy. Most things in our universe are matter. Give me some examples. Air. Great. What else? Lead. Me. Cat. Ice. Great. Carbon. Perfect. Okay. I like it. You guys have all found some examples of matter. Awesome. How about some of energy? Energy is a little bit harder to think about. But we have some very obvious examples. Yeah, so we said photons, which is, for us, light. Heat. Electrons are actually going to be matter. Rocks are energy, huh? Unless maybe it's like delayed for you. Rocks would definitely be matter. Electrons are also matter. Those are going to be particles. We're going to see that those do take up space, and they do have actually a small amount of mass. So really our forms of energy here that we can kind of think about are going to be light and heat. Those are kind of the main forms of energy that we have in our universe. We can talk about classifying energy as well, which we will later today. But typically when we think of energy, gravity. That's a force. It's not really energy. Yeah, whatever. We can put it there. I mean, it's technically a force, not necessarily energy, but it definitely does not have space or mass. No worries. Okay. Let's look at these further. So, let's go ahead and talk about... We can talk about air, carbon, ice, and the cat. Let's talk about these four things specifically. Let's see. So these are all examples of matter, right? They have a mass and they take up space. What's different about these two? Or rather, these four. If we look at, for example, carbon and ice, what's different about those? How can we classify... So we could say both of these are one thing, right? Carbon is one thing, ice is one thing. Both of these are one thing. Let me move that a little bit closer. Yeah. If we know the formula for carbon, it is that. Carbon, C. However, ice's formula is H2O. So you're talking about some physical properties. Yeah, they totally have different temperatures, freezing points. Yeah, absolutely. But just more like, yeah. We're looking at these chemically. So we're going to see that carbon is an element. Element. And water is a compound. So we're going to see that one type of atom will be how we're defining our elements, and more than one type of atom will be a compound. So let's take some examples here. Here's 5 substances. Let's see if we can classify these as elements or compounds. What do we think about Au? That's gold, by the way. What do we think about gold? Element or compound? Yeah, for sure. Easiest way to see if something is an element? If it's just got one symbol, for sure, it's an element. We could also see, if we were to look at the periodic table, we would be able to find Au on there. No problem. We would see gold is on there. Yeah, so hydrogen chloride would be a compound, exactly. And how did you know that? See buckets. How did you know hydrogen chloride was a compound? Yeah, it's 2 different elements, exactly. So if we look on the periodic table, we're not going to see hydrogen chloride. We're going to see hydrogen and chlorine separately as different elements, but once we put them together, that's a compound. Yeah, capital letters is kind of your clue. If there's multiple capital letters, then yeah, it's going to be a compound. All right, how about H2? Hydrogen. Whoops. Yeah, hydrogen is an element, so I was not able to trick you with that 2 there. Definitely, both of those are hydrogens. There's only one type of atom there, even though there's 2 of them. That is going to be an element. How about sulfur? I mean, I guess I can't really see if people are actually writing new things. I'll just tell you it's an element also. Does not matter how many there are, they're all the same. They're all sulfurs. Yep, absolutely. So that is element. Okay, and then how about carbon dioxide? Yep, that's where we're going to have a compound. Okay, so we're going to be able to distinguish these by looking at if there are multiple different types of atoms or if it's just the same atom. Doesn't matter how many of each there are, as long as there's just one atom, it's an element. As long as there's multiple different types of atoms, it's a compound. Cool, cool, cool. Okay, so moving on now, let's go ahead and talk about the air versus the cat. Neither of these are compounds or elements. Unfortunately, we cannot find cat on the periodic table. Does not exist. Unless you're like saying carbon astatine or something, but no, just a cat like the animal, I assume. What's different about these 2 things? So we can agree, first off, that these have multiple components, right? We can see that air has nitrogen, oxygen, argon, water, carbon dioxide, whatever. Yeah. Versus the cat, which also has water and glucose and various proteins and stuff and calcium hydroxide, I don't know. Yeah. So Kevin has already read ahead. We're going to see that air is homogeneous. And so that means that in a relatively controlled setting, say for example this room that I'm in, if I take a breath where I am right now, or if I move over here, take a breath over here, I'm still breathing the same mixture. The composition of air is the same no matter where I am in the room. Okay, unless, one of the dogs decides to fart or something, then we're going to have a heterogeneous mixture. But for right now, it's homogeneous, right? So every part of it is the same throughout. Okay, however, with our cat, or perhaps the dog, we see... Come here, Oz. Okay. With Oz here, we see there are different parts. So, for example, on one part of his body, he has a tongue, right? It's pink, it's got a certain amount of water, various proteins, different types of cells. And over here, he's got an eyeball, wherever that is. That eyeball is also different from the tongue, right? These are different areas. This part is an ear. It has wax. It has other things. All right. If I were to, hi, sweetheart, you want to sit on daddy's lap? Okay. We're going to see that this is called heterogeneous. And how we're going to kind of describe these. Okay, he wants to get off. One sec. There you go. Uniform throughout. Whereas this is non-uniform. And by uniform, of course, I mean it's the same or it's not the same throughout. Alrighty, so who wants, or let's look at a couple more examples. Couple of examples here. So thinking about steel, that's a mixture. Do we think that steel is going to be uniform throughout or non-uniform throughout? Oh, Oz, calm down. Hold on, let me go get him. Oz, come here. Okay. Yes, it's going to be, ideally it should be uniform, right? Maybe in reality it's not, but let's just say for right now it is uniform. So that would be homogeneous. Did I spell that kind of right? Yeah, I think I did. Good. All right, how about honey? Mixture of water and fructose, little bit of glucose in there also. Yeah, that should also be homogeneous, right? It should be the same throughout. All right, how about ice water? Yeah, ice water is going to be heterogeneous because we're going to see that we have, chunks of ice at the top. We have, presumably no ice at the bottom. If we were to take a sip of that water, it would be different depending on where we took a sip, right? Oz, shut. He gets mad if I pick him up. He gets mad if I don't pick him up. So, sorry, you'll have to deal with the borking. So yeah, ice water will be different depending on where you're taking, a sip from. It's a kind of a easy way to kind of tell if you have a homogeneous mixture or not. If you're tasting your honey, it doesn't matter that it's all the same compound, but it is different. It's a different mixture. We have different states of matter in the same mixture. So that's a very good kind of observation that you've made there. We do have water in solid form as well as water in liquid form. And so those two are technically not the same right now. Those are going to be put together to make a mixture. Okay. And then our salad, what's our salad going to be? Yes, absolutely. Yep, and then your salad, of course, will also be heterogeneous. Okay, because, kind of, again, the easy way to tell, if you were to take a bite of the salad, it's not going to be exactly the same as your next bite of salad. Maybe you're going to get more croutons, maybe you get more tomatoes, or whatever things you put in your salad. So, cool. So, kind of in conclusion of this section, we can say that matter can be divided into what are called mixtures and pure substances. And all of these can be divided further. We can say pure substances were either elements or compounds, and mixtures were either homogeneous or heterogeneous. All right, and we define pure substances as kind of like one thing, whereas mixtures were multiple things. Including different states of matter. So if we had, a boiling pot of water or something, we'd have steam pockets that would also be heterogeneous. Okay, so we can classify matter first as pure substances or compounds. Pure substances or mixtures. Pure substances we can define as either elements or compounds. And that's one atom type. And that's multiple types. Homogeneous were the same throughout. And these were kind of different throughout. So kind of for this section, I would expect you to be able to classify something as one of these four categories. Okay, or as a pure substance or a mixture. Don't ever tell me that like an element is homogeneous, because it has to be, that's just silly. Only mixtures can be homogeneous. Okay, compounds and elements by themselves are pure. There's no point in being homogeneous or heterogeneous because they have to be the same. Like they're by definition that way. Okay, and just, that sort of thing you should be able to identify. Okay? Any questions on classifying matter? Yep, absolutely. That is absolutely correct, Karen. And if you were to think about the boiling water, if you were to look at it, you would see certain areas have more bubbles, certain areas have fewer bubbles. That alone makes it heterogeneous. For example, this morning, since we were doing essentially the same thing in 101, they had me pour a soda, and you can see that I have more bubbles on top than I do down below. And that, again, will make this a heterogeneous mixture. However, as soon as this becomes flat and there's no more bubbles, it should be homogeneous again. So it kind of just depends on the state of things. And technically, if you were to look at air, on a global scale, that would be heterogeneous, right? Because we're going to have clouds in some areas, we're going to have rain, we're going to have soot that's falling, we're going to have, all sorts of different things. However, on like a smaller scale, air will be homogeneous. So there is some, distinction here, but by and large, we're talking about things on a relatively small scale. Okay? Any other questions? All right. Cool. So, let's go ahead and talk more about matter. So, we know matter comes in several flavors, right? Look, we have another visitor. Come up here, dude. Come on. Up. Come up here. Come on. Get your booty up here. There you go. There's one of my bigger dogs. This is Kaladin here. Yeah, so ice should just be one thing. So that's just going to be solidified water. Just like if you were to have a bottle of water, that would also be homogeneous. So, yes. Hi, little dude. I guess you're not so little. So, yes, he's just going to lick me. Okay, go on. Go play. States of matter now. What are the 3 states of matter we're going to be discussing in this class? Oz always tries to kill him. Here we can watch. Where did Oz go? Okay, well, I guess we're not going to see any death matches today. Yeah. I'm just going to reorder those a little bit. So we have solids, liquids, gases. Of course, we do have plasmas and other things, but we're not going to talk about those here. You can deal with those in like physics class or something. Cool. So let's think about solids. How do we know if something is a solid or not? While you answer that, I'm going to just send this guy outside because Oz will just keep trying to kill him. Come on, let's go. Come on, Calvin, go. Good boy. Go on, go. I know, Oz, you're canicidal. Yeah, okay, got some good answers so far. So solids absolutely have a defined shape, right? This stapler is going to look like this. I guess this is not really a pure substance, but whatever. Yeah, it's going to hold its own shape, okay? And I like another one that was written was not compressible. So we cannot, take this bottle cap and try and, squish it together, try to compact the atoms. It's just not going to work, right? I can't do that with a rock. I can't just squish them all to make it a smaller rock, Doesn't really work so easily that way. Okay, let's see. Closely packed together. Yep. So the atoms are close together in solids. And they're kind of, not really mobile. Let's say not... Ugh, it's so hard to, actually write these. Atoms not moving past each other. Moving around. So they are vibrating, technically. The atoms are just like... But they're not like... So they're not really moving past each other. They're just kind of vibrating in place. All right, and one more. Let's see. Rigid, that's pretty, we can say that for most solids. Yeah, that's fine, Pack closely, yep, got that one. How about, let's see. If I take our friendly stapler... I like where you're heading, Susanna, but I want something a little bit different than that. Because all of these technically will have defined mass. If I take my stapler over to my other hand, it's now in a new location. Does it occupy any less space than it did before? I will now move it here. Yeah, exactly. That's what we're going for. We have defined volume. So it's not going to take up less space in a different area, right? This stapler will always take up the same amount of space for as long as it is solid. Okay, cool. Let's talk about liquids now. Do liquids have defined shape? Look at Kevin here with all the answers. Kevin is absolutely right. Water will change its shape depending on the container that it's in. So right now, I guess this is spindrift, but like the liquid in here is in this cylindrical shape. If I were to pour it all out over the floor, which would be a stupid idea, it would completely just move all over the place. It would change its shape. However, it will not change its volume. Okay, I'm going to just have to write gases on a separate thing just because I don't want to run out of space here. So look, if we look at these two are kind of the same. Okay, I lied. They are definitely moving around. Okay, fine. Okay, atoms are still fairly closely packed. That just means they're kind of really close to each other. However, atoms flow past each other. So they're not just held in one area, they're kind of moving around. Definitely not compressible. If I take the liquid in here and try and squish it, it's just going to either break the container or it's going to like squeeze out. It's not going to become lesser in volume, right? Okay, and we can say they're also not rigid, right? Okay, cool. So liquids and solids are pretty similar, right? They have a couple of properties that are different, but by and large, they're pretty similar. All right, but gases, on the other hand, we're going to see, sorry for having to move this over. I planned poorly, not enough space. Gases, on the other hand, no fixed volume, no fixed shape either. So, this means non-Newtonian fluids, get out of here. Shane, you're like taking me into physics land. I don't want to deal with that. We're just going to be talking about Newtonian fluids here, so no worries. I like where you're going, though, but nope, not here. Yes. So gases will completely fill containers. We can see our liquid here does not fill the container. And it's an open container too. So this whole area is not occupied by the liquid. However, it is occupied by the gas. So the gas in this room has filled the shape of this room. And if I had a tank of gas, it would also fill that amount. Yeah, so we're going to see that the atoms are super far apart and moving quickly. Yeah, absolutely. So they're totally moving around. Not necessarily. We're going to be talking about gas laws, I think, in chapter 9, if I remember correctly. And we'll talk about how expansion and contraction work with gases. That's more to deal with pressure and just work that they're exerting on their container in the environment. So we'll leave that question for a few chapters from now. Okay. Let's see. Anything else? Yeah. So we can see that because they're super far apart, we can compress them quite a bit. We can take a lot of gas and put it into a relatively small area. For example, you've seen a gas tank, maybe you've seen the movie Jaws, there was an oxygen tank that the guy blew up that had a lot of oxygen within it. And so, as soon as that opened up, it was the explosive, right? It was a lot of gas kind of spreading out at once, does a lot of work, and I'm sure there was some combustion there as well. But yeah, there's definitely the compressibility factor with gases. Okay, so we see like solids and liquids pretty similar. They have their fixed volumes, they're fairly rigid, they have their atoms close together, but gases are pretty much the opposite. Gases are really far apart, they don't have fixed volume or shapes, you can push them together really easily, and they're really moving around quickly. But in liquids and solids, they're just kind of like swishing past each other or just not like kind of vibrating in place. So gases are kind of our most extreme case of these states of matter. Okay. Is that okay so far? So if I were to draw some atomic structure, or not atomic structure, but just atoms. We can kind of display these, right? So if we were to look at the one on the left, what do we think that one mostly corresponds with in terms of atoms there? Yeah, that's most likely a solid, right? And in fact, we can see that this one has relatively orderly, systematic kind of organization to it. This is probably what is called a crystalline solid. That means orderly, structured. It's very kind of uniform, right? This one in the middle, though, what do we think that's going to be? Yeah, that's probably a liquid. Or it could be an amorphous solid. And this one is just going to kind of depend if the atoms are flowing. So if I draw little like arrows here, whatever, that's going to probably indicate it's a liquid. But it could be what's an amorphous solid. Amorphous solids are just not orderly solids. So something like glass, the molecules are just kind of thrown in there. It's just solid, but things are not moving. And it's kind of disorderly. There's not really a fixed repeating order. But it just depends if the atoms are moving, flowing past each other or not. Okay, and the last one, of course, is going to be our gas. We can see the atoms are really far apart from each other. Chances are they are moving very quickly, and that's going to be what kind of gases look like. Okay. So that should be hopefully nothing terribly new for you guys. So we're going to do one more little bit. Yeah, amorphous solids versus crystalline solids. You know what? Let me see if Wikipedia actually has better images of these. Just atomically. Oh, here we go. Beautiful. Okay. So let me go ahead and show this screen. Yeah, that one. Okay, can we see this? I hope so. So this is kind of the difference between an atomic solid or a crystalline solid right here. Everything's orderly and fixed and nice. Whereas in the amorphous solid, things are still it's still a solid, but things are just more disorderly. We see that this has these nice, hexagonal shapes going on. This one's things are just kind of chaotic, right? So this would be in a amorphous solid, something like glass, whereas this would be something like a crystal, like a salt crystal or something where we have, sodium chloride, sodium chloride, sodium chloride, but it's all nicely arranged together, where things are neat and orderly. Okay, you can see some more examples here. Orderly and nice crystalline. Amorphous is going to be more kind of, spread out over the place. Okay, back to, oops, not that one. Let me close this window. Aha, cool, awesome. So does that make a little bit more sense about the amorphous versus crystalline solids? It's just kind of how orderly they are. Okay. So the next thing we'll talk about here, again, this kind of first chapter is kind of all over the place, just because it's kind of laying some foundational stuff. So I know it's going to seem kind of disorderly, but that's okay. We can see matter can have properties that we'll talk about. We can describe certain components of matter as having properties. And I'll tell you one of these properties is the state of matter. We can identify, whether this water is in a liquid state, a gaseous state, a solid state, or a combination of those. We can see what that property is. So these are just kind of things that we can observe about matter. So if we think about other things we can observe, what else? Jelly. Jelly's a tougher example because that's a mixture. Typically, we talk about pure substances when we talk about states of matter. Probably it would be an amorphous solid. That would probably be the closest. It could be a liquid just depending on the temperature. If you put the jelly, from its container onto the whatever pancake and it spreads out, then it might be a liquid. Kind of just depends on the temperature there. But it would probably be one of those two, yeah. So besides the state of matter, what else can we identify? For example, this bottle cap, it is solid. What else can we identify about it? Describe this to me, this piece of matter. Yeah, it's blue, right? It has color. Yeah, that's definitely one. What else can we identify about this thing? Yes. It's definitely matter, so it certainly has mass and volume. It does have density. Sure, we can say that. Shape. Freezing point. And therefore boiling point as well. I'm just going to write one of them. Hardness. Conductivity. Absolutely. What else? Weight. I'm going to go ahead and just put that one with density. We'll keep those together. Weight and density are very similar. How about location? It's in my hand right now. That's something I can observe. Yeah, flammability. Absolutely, another one. Composition. It's not necessarily a property. That's something more like just kind of a characteristic of it. So it's not really a property, as it were. Solubility, yep. And just to throw some more out, we can talk about malleability. That's, for example, how easy it is to flatten, basically. We have flexibility. These are all flexibility. Definitely good properties here. Reactivity, yes. Okay, I think we have enough properties for now. Odor, yeah, sure. Yeah, why not? Let's put odor in there. Alrighty, lots of properties. I'm going to tell us that these ones here are all one category of properties, whereas these two are a different category. These ones are physical properties. So these are things we can kind of easily identify. It's blue. We got it. It's in my hand. It does not dissolve in water. It doesn't really conduct electricity. These are things we could determine, either we have to use an instrument to do it, or we can just determine with, our naked eye. Freezing point we could identify by heating this up, seeing when it melts. So these are our physical properties. Okay, these two, on the other hand, are chemical properties. These describe how it interacts with other components. So, for example, flammability is a chemical property that tells us about a substance if it will undergo reaction with oxygen. So is this thing going to burn very easily? Probably not. Plastic doesn't typically burn very easily. However, let's see. This J&J dog supplies thing that's made of paper will probably burn really easily, right? These two have different chemical properties. Of course, they have different physical properties too. This is a different shape. This is, different whatever, right? So totally different things here. We can see that maybe this will react with sulfuric acid, this will not. Those are going to be chemical properties. They're going to talk about how things will react chemically with other things. We can see also that we can mess with these properties. If we mess, or let's just say alter, if we alter a physical property, it is so hard to spell when oxidation level, that is a chemical property as well. Yeah, absolutely. If we alter a physical property, that is called a physical change. Let's see if we can think of some ways of messing with our physical properties. We could melt something, for example. We could take ice and melt it into water. We are changing its state of matter. State of matter was a physical property. We could move something. That's also changing a physical property. Yeah, we could cut it in half. That would be changing its shape, right? Or its size or something. Definitely a way of physically changing it. Some of these are not so easy to change. We can't really change the conductivity, but we can change some of these things, right? Notice that if I were to melt the ice or move an ice cube from one area to another, or if I cut an ice cube in half, they're all still the same. And the most obvious example is moving it, right? If I move my, bottle cap from one area to another, is it still a bottle cap? I hope so, right? We can see that these are also relatively easy to reverse. If I melt my ice cube, I could freeze it again, right? It's fairly easy to do that. If I were to move the bottle cap from one place to another, I could move it back again. If I were to take, what is this? Some wedding invitation, I could bend it, right? I'm changing its shape, and I could unbend it again. Poof. Physical changes are pretty easy to undo. So physical changes do not alter the substance. It's still the same substance, and they're relatively easy to reverse. Okay? Chemical changes, on the other hand, are going to be like if we burn some wood, and we burn it. So you tell me, Star-Lord, if I take this piece of wood and burn it, can I take this CO2 and water and soot and ash and put it back together into a piece of wood? No, not really, right? I mean, it is possible. Like, technically, a plant does all this stuff. It takes CO2 and water and will convert stuff into... So, like, yeah, Satori, it's interesting. Like, cutting it in half, like, technically, it's not as easily reversible, but, like, it's a lot easier to put this invitation back together than it is to put this wood back together. Right? Just thinking of relative ease. Like, you know, I could kind of align it to again, and now it's kind of okay. But the wood will never be the wood log again. Okay, this is almost impossible to reverse, if at all. Extremely hard to reverse. So this was a chemical change. Okay? And if we look, is the wood still wood after we burned it? No, it's not wood anymore, right? It's now carbon dioxide and water and soot and ash and all these other things, right? It's not wood anymore. Okay, and it's also changes the chemical composition. Okay, so the wood is no longer wood. It is now these other chemical components. Okay, and it's very, very difficult to put these back together again. If we somehow had some crazy energy source, we could maybe put these things back together and form the wood again, but not likely. Right? A plant can do it. The plant has done it. It took all these things and put them together to make wood. But that took a very long time, right? It took very many years with a lot of solar energy to make these things into wood, and burning it has kind of really ruined that. Okay, physical changes, relatively easy to undo, and don't change the substance. Okay, chemical changes, on the other hand, hard to undo, and they do change the substance. We're making something new. Okay, another example of a chemical change. How about iron going to rust? Yeah, photosynthesis is definitely a chemical change. We're turning carbon dioxide and water into a glucose, right? And oxygen. So we are undergoing a chemical reaction. That is a chemical change, for sure. So this is typically how we could talk about iron rusting in terms of a chemical reaction. Typically, Savannah, light is not going to be a reactant because we don't really think about those, think about energy as part of a change because it's not matter. Matter is what's undergoing these changes. So it's properties of matter that are being changed, and as a result, that's the thing. Yeah, so this is, the iron to rust is definitely a chemical change, right? We have iron on one side, we have iron oxide on the other side, two different chemical compounds. That tells us there's a chemical change. All right, and by itself, that rust is not going to turn back into iron, right? It's not going to happen. However, if you were to throw it into a solution with a lot of electricity and certain things happening, we could get it to turn back into iron. But again, we have to do a lot of work. It's not going to happen by itself. It's very difficult to take that rust and turn it back into iron again. So definitely a chemical change. Okay, so hopefully those are pretty clear. So yes, it certainly did change its physical properties. It's a different color now. Yeah, because it's a different substance, for sure. So, like, rust is kind of that orangey red, whereas iron is kind of that silvery gray color. And now, yeah, that iron was hard and malleable, and the rust is brittle and soft. So, yeah, since it's a different substance now, it will have different properties. Alrighty. Any questions on that? Or anything else we've talked about? Maybe, talking about solids and liquids has gone out of your head now. Since we only have about 5 minutes left, I don't want to introduce like a new topic right away. So if there is nothing, I think we'll just be done for today. Okay, one thing I do want to show you in Discord here, I think that is this window. No, it's not. Where is Discord? Was it this one? Ah, I found Discord. Okay, I'm going to make another channel for us. And I'm going to be posting the lecture notes here. I'm just going to make it so you guys cannot edit it. You can read stuff, but not. Actually, you guys can read, but not send. Okay. Oh, yeah, save. Okay. So I'm going to be saving these notes up there. So all the stuff that I've written down. Miranda, typically, if it undergoes a chemical change, it has to change its physical properties too, right? Because it's a different substance. Let me see here. Let me just get this going. If we're changing our wood into carbon dioxide and water, I hope this is to the right one. I hope I didn't put it. Let me just edit this so it's easier for me to see. Okay. So awesome. Okay, so this has loaded into there, so you guys will be able to see the lecture notes that I've written. You'll be able to download those if you want to. Okay. So does that answer your question, Miranda? By the way, like a chemical change must accompany physical changes. Like if we turn copper metal into copper 2+, it turns from coppery colored to blue. Totally. No. So I would go with whichever one is more accurate. So if it's a chemical change, like something burning, put chemical. Because physical changes, right, they don't accompany a composition change. So, like, yeah, you'll observe different things, but that's because there are different compounds there. There is no homework yet, Kevin. However, I'm going to post something in Canvas for you guys. I do want you to start looking at it. It's going to be our metric system prefixes. I just want to get these kind of familiar in your heads. So I'll post that in Canvas, so you should get something. I'll also post it here in the lecture notes, I guess, just so you can see that. So yeah. Alrighty. Any other questions? So yeah, just in your Chem C111, you'll go to lecture notes. You'll be able to see this. It'll download the like pretty colorful stuff that I've done today. Alrighty. So with that, I will see you guys tomorrow. So take care, stay safe, be happy, enjoy your Tuesday.